Okay, but while we're waiting on that, I'm going to go ahead and start doing a little bit of a review for the quiz that's coming up. So we started off with this chapter on energy with the concept of work. And we said work is the transfer of energy by means of a force applied to an object through a displacement. And there has to be some part of the force and the displacement along the same line. Which means that if a force is applied to an object and the motion is all perpendicular to the direction of the force, there's no work done. So to take care of that, we gave you a formula that said work is the product of force times displacement, which we called S or delta S, times the cosine of the angle between them. Now that takes care of this whole issue of everything being in the same direction. Because if the forces and the displacement are along the same line, then this will be the cosine of 0 degrees, and the cosine of 0 is 1. If they're perpendicular to each other at 90 degrees, this will be force times displacement times the cosine of 90 degrees, and the cosine of 90 degrees is 0. So there's no work done if the angle between force and displacement is 90 degrees. Right? So that is an important thing for us to be aware of. So if as long as there is some force that's along the line, what's going to happen to the object's motion? If there's some component of force, and this is net force here, if there's some component of net force, then the object's going to do what? Move. No, more specifically than move, it's going to, force is equal to mass times acceleration is going to accelerate. So it might already be moving, and then a net force wouldn't keep it from continuing to move. But it's going to accelerate. It's going to change its state of motion. If it changes its state of motion, something else changes. And the other thing that changes is the kinetic energy of the object. And this was that old formula that you had, one that you knew from 8th grade probably. But the kinetic energy of an object can be found by multiplying 1/2 times the mass of the object in kilograms times its speed in meters per second, and that quantity has to be squared. So, if we have work done on an object, this is going to change, right? Because the object is going to accelerate if work is done on it. Velocity will change, and therefore kinetic energy will change. And that gives us what's called the work energy theorem, which says that if there is net work done on an object, it will change the object's kinetic energy. That was the work energy theorem. Remember that guy? Okay, so this is one type of energy, the energy that an object has due to its motion, but there was another type of energy due to an object's position. What was that? Potential energy. And really we're talking about gravitational potential energy here is the only kind we're talking about. There are others. Potential energy occurs when a certain kind of force called a conservative force, we'll talk more about that later, but a conservative force acts between two objects. Which means energy is stored in the interaction between the objects. And so, for one example, that is energy stored in a rubber band. Because in stretching the rubber band, the two objects that stretch it are storing energy in that interaction with the rubber band. Gravity is the same way. When an object moves, when two objects move towards each other or away from each other, the amount of energy stored in their gravitational fields changes. So when the objects are close together, they have less energy. When they're farther apart, they have more potential energy. The potential energy, gravitational potential energy, can be found by multiplying what? Everybody, what's the formula? mgh. Okay, now what does that mean? M is the mass of the object, really one of the objects. In this case, we're talking about the other object is what? What's the second object that we... Earth. It's Earth, right? And so the second object is hidden inside that little g. Remember that little g can be written out as a big complicated formula, but the Earth is in there. So the potential energy between these two is the product of the mass of the object, the gravitational field strength of the other object, the Earth, and the distance between their centers. So potential energy, whenever we are looking at this, we are always really looking at a change. Now we aren't always careful to write that out, but we're always talking about a change from one distance to the center to another distance from the center. So this, and in the case of potential energy, this is the thing that's always changing. Now we don't always write the deltas out, but that's what we're that's what we're dealing with here. And so if we have if we want to find the potential energy of an object that is in two different positions, and we want to compare those changes in going from position A to position B, then what we can do is just set the lower of the two at 0, in which case we would say in the beginning the object had no potential energy because we set the height to 0. But the higher position would then be measured between the two, and that would tell us the difference in potential energy from the lower position to the higher position. And you could be going the other way as well. But either way, you always set the lowest one at 0, because that way you're always just finding potential energy between those two heights. So when we next talked about energy, we talked about the conservation of energy between really mechanical energy, potential energy, kinetic energy, and work. So the conservation of mechanical energy gave us this problem, this formula. We had kinetic energy original plus potential energy original plus any work that put energy into the system, so we call that work in, is equal to the kinetic energy the object has afterwards, so we call that Ke sub F, plus the potential energy the object has afterwards, plus any work that took energy out of the system, minus this. We do minus if we want to, so if we want the formula to always give us a negative work for this value. And so we're just putting it at negative to begin with, so that if we calculate the work, oops, I wrote in. Did I say in or did I say out? Work out. So because work out is always negative. Remember, another fact that's very important about work, energy are all scalars. So positive and negative do not denote a direction when it comes to work. What do they mean? Positive means what? The amount of energy is increasing. And negative means it's decreasing, but it has nothing to do with direction. Vectors, it's all about direction. Okay, so far, so good. And these problems that you had on the last assignment are all about this, right? They're all about conservation of energy. Shall we do those now? Are you ready? Or
No, it's fine.
Okay, so nobody else needs to see any of those? We're good to go on that? Remember, because if you always do what I said and always set the lowest position at 0, then you'll only have potential energy on one side or the other, whichever one's not in the lowest position. So you'll never have all of these things. I mean, you could have theoretically, but I would not give you one that complicated. So we're good to go on that. Then so let's then go on to the next topic then, and that's the topic of power. Power is the rate at which work is done or the rate at which energy is transferred. So it will be either work divided by time, or it could be one of the types of energy. It could be potential or kinetic energy divided by time. So I will just put energy divided by time. Okay. So this is another rate. Physics is loaded with them, right? And this is the rate at which you do work, or the rate at which energy is transferred between two objects. And the unit of power is the
Kilowatt.
Watt is the base unit. The unit is the watt. And you can tell me by looking at the formula what the unit is made up of. Work is measured in joules. So this is joules per second. Right? A watt is a joule per second. Okay, let's go back to our base units again, because that's something that you really need to understand. And if you know the formulas that you can analyze to find them, then you can always find what the base units are. So what is the unit of force in the SI system? The Newton. So let's look at units here for a minute. So this is a compound unit. That means that base units have been put together to make this unit. And we need to figure out what base units make it up. Okay, so what is a Newton equal to? Kilograms.
Meters.
And meters.
M squared over second squared.
Not squared, just M. Divided by second squared. Where does that come from? It comes from the formula F equals MA. Right? Force in newtons is equal to mass in kilograms times acceleration in meters per second squared. So if you just remember this formula, which by now probably is ingrained in your brain, you can deconstruct the units here, kilograms, meters per second squared, to find the base units hidden beneath the Newton. Okay, while we're at it, let's go on and say, what is 1 joule equal to in base units? Now, there are a couple of ways to go about this. You might look over here at, this is going to be what units for the force? You just said it.
Kilograms
Newtons.
times.
Kilogram meters per second squared. Times this displacement, which is meters. So the only difference is going to be the meters will now be squared as well. Okay, now really the better formula to find this in is the kinetic energy formula. Because the kinetic energy formula is 1/2 mass times velocity squared. And so mass is kilograms, velocity is meters per second, square it, and you get meters squared per second squared. And so this formula is the one that will most easily deconstruct to give you the base units inside the joule. Link just to the watt. So a watt is a joule per second. A joule is this. So a watt is a yes,
Kilogram times meter squared second cubed.
per second cubed. Excellent.